Okay, on to the last problem, question 5. So we're given some information from the debugger on the right there about some addresses and the code in the stack, and then some information about our shell code and where the input is stored in memory. And we're going to use a malicious return address um, of a particular value a single time. So this is a buffer overflow attack question. We're trying to figure out what the stack looks like and does this attack work, and then some other details about it. So part A, how many bytes are between where the user input is stored and the user function EBP? So we have to look back actually. It's helpful to think about the prior question where we had our diagram of what's in memory. And these values aren't correct for this particular problem, right? But the general outline of the stack is still useful here. So if we look at what our stack generally looks like, right? We've got user function variables and we've got our buffer somewhere in there, right? And then down below that is EBP of the user function, which is the prior EBP, and then the return address after that location in memory. And so what we can kind of derive from that is that EBP of the user function is where our sort of prior EBP is stored in memory. And really, we know that like EBP is the end of the user function variables. So therefore, if we use this value as our sort of end of the space, and the value we're given the location of that buffer in memory as the beginning of the space, then the space between that is how many bytes we have. So we need to do some hex math. So OXBFFF uh, 5, 4C is the value I'm taking from EBP there, minus OXBFFF 4EC. You might notice here that a lot of these questions, we can just ignore the first part of this since it's all going to cancel out, right? And just sort of look at the last couple digits just to save us some time. So C minus C is 0. 4 minus E, we can't do yet, so we need to borrow. So that becomes 4, which is going to end up being 0. And then we have 16 is what we borrowed, plus 4 is 20, minus E is 14, and so that leaves us with 6. So we end up with OX60. And if we think about what the hex format looks like, that's 16 times 6 plus 0 is going to be 96 bytes in total. So that's the space that we have on our stack here, or in that particular stack. Part B, what is the minimum size of an attack, including no-op exploit and malicious return address? So to do that, we need to overwrite all the space from buffer down through prior EBP and return address. And we can see on the prior question, right, there are 4 bytes in prior EBP and 4 bytes in return address. So we have our 96 bytes for the previous question, which is the space between buffer and the end of user function variables, plus 4 bytes for prior EBP, plus 4 bytes for the return address, and that leaves us with 104 bytes total. Okay. Your shellcode exploit is 80 bytes long and you are using a single malicious return address. What is the minimum size no-op sled you need to perform this attack? So I can get rid of this other diagram now, and we can just sort of think about it in this context. So we have 104 bytes for our entire attack. We're going to use 80 bytes of that for the shellcode exploit, right? And then a single malicious return address is another 4 bytes. And so we're subtracting 84 out of 104. That means we need 20 bytes of NOP sled left over to perform the attack. Part D, will your attack succeed with the current malicious return address of BFFF-F4DF? So it told us that earlier in the question. That was our malicious return address we were going to use. Why or why not? So we need to think about it in the context of what this looks like. We know we've filled up enough space so that our malicious return address is where it's supposed to be, right? So we need our malicious return address needs to overwrite the real return address. That's one of our are sort of constraints on this. So the malicious return address must overwrite the real return address. Otherwise, this attack's not going to work. So we did that. Check. Now it's going to go back up, and we need to land somewhere in the NOP sled for this attack to work. Or at very worst, we need to land at the very beginning of the shell code, right? So we need to know what those addresses look like. So our NOP sled is going to start where we said that our buffer starts, right? Because that's where we can start putting input in. That's where our initial input is going to go. So that's at OXBFFFF4EC. And then we have 20 bytes of NOP sled. So we need to figure out what 4EC plus 20 in hex. And 20 in hex is going to be 1, 4. This is 16 plus 4. So 4EC plus 1, 4. We have 0 here because that's 16, carry the 1. And we have E plus 1 is F, plus 1 is, again, 0, carry the 1. So it's going to be 500 in hex. So our NOP sled ends at OXBFFFF500. And so that's the range of addresses that we can target with our malicious return address, so that when it goes back, it can go to, somewhere in between there and still end up hitting the shell code the way we want it to. So will it succeed with 40F? We just need to compare this 40F to the values we have here. We can see that that 40F is actually somewhere like up there. It's not within the range of the NOP sled that we have. So no, it is above the NOP sled. So that's the first one. Second one, we're going to use that same diagram, and you change the malicious return address to BFFF508. Will it succeed with this change? Why or why not? Again, we just look at this diagram that we built up before, and we see that that's somewhere in here. That means it's in the middle of the shell code, and that's also not going to work because we only execute part of the exploit. No, this address is in the middle of the shell code. So the entire attack won't run, or exploit won't run. Okay. And then last part, name and describe one of the technical defense methods that could be used to prevent a buffer overflow attack. So you can choose your, favorite one, canary, ASLR, or non-executable stack. So I'll say, ASLR randomizes addresses. So it's harder, but not impossible, to select a correct malicious return address. So something like that, as long as you pick out one of the ones that we've talked about, that should be good. So hope this helps. Good luck preparing for the exam.